So I believe we are now going to cross across to New Zealand for the second time today. And it's Michele Bannister, a targeted survey of approaching interstellar objects with CFHT. Michele, it's not easy for me to interrupt you since it's remote, so please try to keep your talk to about 12 minutes so there's time for questions.
Lovely, thanks. Can you hear me okay?
Yes, we can.
Kia ora tātou, everyone. So one of the things I'd like to say straight off the bat here is thank you to CFHT and the community for making this hybrid, because this is one of the things where, as you start to get towards mid-career, folks, particularly women in science, it's often a lot harder to travel to these conferences than it was before. And sometimes for women in science, you're not medically allowed to get on planes. So this is, really makes it possible to stay in touch with the community and be able to keep using the wonderful telescope that we all know and love. So what I'd like to go through today is this project that is a team effort across Canada, France, Taiwan, myself and the team in New Zealand and the UK, and also in the US with Joe. So what we're trying to do here is look at a very different kind of population than you might often hear from solar system surveys. And this is the population thought of as interstellar objects. And just to do a quick recap for those of you who don't think about them as much, this is planetesimals that we have from any star in the galaxy, or for that matter, from other galaxies. And so we sample them when they come through the observable volume of the solar system. One-eye Oumuamua was the kind of type definition one. We've since had two-eye Borisov. But these are a really interesting population because if they're coming from every star that has a planetesimal disk in the galaxy, then they form an incredibly numerous population. And so we have two at the moment in the observable sample. And that means to try and understand the next ones that we're going to be discovering with CFH and upcoming sky surveys, we first need to have a really good theoretical model for this population. And that means that I have to go from talking about something that's a solar system survey to talking about the galactic population. So this is something where these are a population that outlive their origin stars. They are a tracer of the galaxy's star formation history, but also its dynamical evolution. So we have this linkage here between small body studies and galactic studies. And so for the last 5 years or so, we've been trying to put together the Ōtautahi Oxford model, which gives us a population model that we can actually test. So this is, to give you a brief overview of where we're at so far, the most interesting couple of things I think we've managed to pull out of the modelling to date. Because we have to be able to provide an inference model that's going all the way from disk chemistry through scattering history of a planetesimal disk and say a giant planet instability, all the way through to the dynamics. So I'll focus for a moment on the dynamics side of this. So this is the paper that we just had accepted a couple of weeks ago, and this is led by John Forbes, postdoc in our group. And it's a semi-analytic approach to describing the positions of interstellar objects as they come off their progenitor systems. So that could be an individual star, or it could be the product of the cluster of stars in a birth cluster. And so this semi-analytic approach lets us get to effectively arbitrary precision spatially, depending on how complex we make the potential that the stream of each progenitor is orbiting within. So this is a package, you can install it. LB Particles, we have a paper up on the archive describing that as well, which has just received its review. So this product of streams means that the amount of interstellar objects that you sample at any point in the galaxy is complexly determined by the dynamics as well. So if you look at one of these streams here in detail, So here we've got 10 to the 4 particles, and this is sampled with a very nice kernel density estimator that John put together. So have a look at that in the appendix of this paper if you're interested, for being able to sample how particles move in this galactic potential. So we've used this for ISOs. Other people have used it for axions, dark matter in the galactic potential. It's quite useful. The ISOs are making streams in perhaps the same kind of context as you think of them as stellar streams. And so you get these really interesting complex density profiles that as the stream wraps the galaxy, braid and have some density with time. So if I then go, what is it like for us, for our observable volume? The sun is in 10 to the 7 streams, which sounds like a lot, but it means that there's going to be quite varied encounter rates that we'll have within the survey observable volume of the solar system. So if I just change the screen share here for a moment, I'll show you what happens when we take into account not just the galactic potential, but the heating of giant molecular clouds. Lovely. So what we're now seeing here is a stream of ISOs that's been generated by our semi-analytic model that's now being integrated in a modified version of GalPy with another 10,000 or so giant molecular clouds distributed. So just to keep things simple, this is equal mass giant molecular clouds. So what you have is the angle around the galaxy, so we're centered on the progenitor. And this is a stream that I'm showing for the moment to show you the behavior of how it's porpoising through the galaxy and evolving, but one that isn't being perturbed by the GMCs. So this is one of those streams I was showing you in the top-down galaxy view. Now, over time, you notice this broadens. It's actually, the broadening is also set by the initial velocities distribution of how these are scattered off the initial origin system. So there's actually a memory of the exoplanet arrangement, the architecture in a system that then goes into forming the stream. It's pretty amazing. Now, if I do this and then have the stream heated by the giant molecular clouds, then you start to see something quite different going on. So the role of heating really does play an interesting aspect in terms of making clumps within the stream. So this is an aspect we've really just started to explore, and building that into a fully galactic model is probably going to take us a few more months. But this is the work led by Angus Forrest as part of his master's thesis. So yeah, it doesn't always centre entirely on the progenitor for where you get the densest regions of ISOs. Now, if I just go back to the other presentation, lovely, there we go. Now, the thing I also want to emphasise is that we end up with a spatial arrangement in the solar neighbourhood that's not just dictated by the streams. Interstellar objects, much like their stars, are going to have velocity structures. They're not going to be distributed by a smooth Gaussian. So if you think of the velocity structure that the potential of the galaxy and all of its perturbations impose on the observable, this is really familiar from Gaia at this point, right? This was one of the great party pieces of Gaia. But to understand how this works for ISOs, we have to debias the stars in Gaia by the fact that interstellar objects do not die. They continue to live throughout the lifetime of the galaxy. So this is the same plot, but with the structures debiased for that to make the ISOs rather than starting with stars. And so if you look at the two known interstellar objects we have, the purple triangle here and the green triangle pointing downwards, we can see that the first interstellar object found was typical. It's part of a moving group, effectively, of ISOs that would be 1 in 5 ISOs we should expect to find are going to come from this group. And 2I is from the second most common group. So the first one we found and the second one we found are from the local velocity structure. And so this will be perceptible in the samples we get from upcoming surveys. So what does this look like on the sky? Because we have a telescope, and a telescope means we can make tests of this kind of theoretical model work. Well, the main thing that dominates this, and this has been known for a few decades now, is the motion of the sun and the galaxy. So you do get a density towards the solar apex, But because of the moving groups, because of those velocity structures, you get a big northern sweep projection on the sky as well. So it's not just as simple as looking at the solar apex. You get a big northern arc to this. And so we went through the archive and went, great, how much data do we have that we could look to check for infalling ISOs, ones that haven't been past the sun, ones that are sampling the pristine potential environment, because we expect effectively no ISO ever will encounter a star close enough to be thermally heated before it reaches us. And CFH and many other telescopes have not looked deep in the regions where our model projects these infalling objects. Okay. Surely LSST will save us. Well, Rosemary Dorsey spent a fair chunk of her PhD looking at the observability of our model in the LSST, and they put that telescope in the southern hemisphere. So for a northern infalling population, it doesn't do as well as you might hope. So we're in a situation where LSST has the sky coverage and the cadence, to a certain degree the depth, not as deep as it could be. But the perihelion distribution means that you're only going to pick these up pretty much equally split. You're not seeing infalling ISOs at the same rate. So we have been asking CFH, can we experiment? Can we put a relatively small test set of fields on the footprint? And we're doing this on the LSST footprint at the moment, partly because that way we get pre-covery to LSST, which will be ideal when in only a couple of months we start getting LSST detections through and we can compare. And so that'll really stretch out the observed arc very quickly. And so this was our 2014 data, has been coming through really nicely. And I want to emphasize we're trying a parallactic survey with this. So this is a spin-off survey in very many ways from Classy. We have, it was inspired by Classy in terms of the pipeline and the methodology, and you heard a fair bit about that from Wes and Sam already. This is the way of adapting these kind of shift and stack moving object techniques to stretch out that baseline. So we're trying, instead of intra-night, we're trying inter-night. And so it's a much more flexible cadence than you might be used to seeing from one of these moving object detection surveys. So we got good coverage on our field in 2024, and our 2025 field is placed out of the plane so that we can start to really calibrate how much the effect of stellar density affects our pipeline, and also just see if we can get a little bit of spatial variation on the expected discovery rates. So even if we got, and I should also say CFH has started getting us data for this year, which has been great to see. So even if we don't find a single ISO as part of this, because we're doing this in a calibrated way where we inject the model into the data set, PSF match, recover it again, we have a characterized moving object survey. We will have a spatial density estimate for interstellar objects, completely independent of Rubin. So where does this come in for the community surveys? Well, this is...
also to wrap up soon. Thanks, Michele.
Grand, thanks. Yep, last slide. So for community surveys, this population's in the north. This population's in the galactic plane. If we look with a reddish broadband filter, R, even G would be okay, we will get these objects on the way in. And the cadence is flexible. ISOs just keep coming through the solar system, so it doesn't matter exactly when you start and end. Where you put it on the sky can be quite flexible as well. This is, I would like to say, a science case that would really complement what we have in mind for the community surveys. Because this is a new field of astronomy. We're combining everything from planetary astronomy through galactic structure and evolution. And I'd love to see CFHT have a role in that. Thank you.
Well, that is super cool. Maybe I could ask the next speaker to come up and start setting up while we take a question. Any questions? I find that hard to believe. Michele, when do you expect, in terms of the program that's underway, is it a case of you could find one of these things at any time, or is it going to be a little while before you have the right cadence and enough exposures to be able to sort of start being, if there's something in your data set, when can we expect a detection?
We're analysing the 2024 data at the moment. We don't quite have enough on the 2025 yet, but we hopefully anticipate having the 2024 field recovered again this year as well. So I would say, we anticipate being able to get an initial detection list or non-detection list out of this, certainly by the time we get LSST start.
Great. Thanks. Let's we better move on just because of time. Let's thank Michele again.